So today I'll be taking on the topic lambda analysis. Okay, so lambda analysis is done on a special case where the solids having a very large thermal conductivity. Normally, all the material it could be even if it is a plate or solid like that, so it will be having a very finite thermal conductivity, and obviously there will be a temperature gradient. Okay, there should be temperature gradient not for the heat transfer between one part of the way to other part. So usually also it will be having a very finite thermal conductivity, and obviously there should be a temperature gradient, so heat can be removed or added, right? So, but for lambda analysis, what we are here considering is we'll be having a material solid having uh, internal resistance very much negligible comparing with the surface resistance. Okay, that's the condition or the uh, basic assumption or not assumption. The basic condition for lambda analysis is the internal resistance of the body will be very much smaller compared to the surface resistance. If you consider a plate, suppose I've shown here a plate, and you know uh, when we add heat on the one part, suppose I am here adding heat to this side, obviously the heat could transfer inside from one end to other end by conduction, right? We already know that the conduction and convection. So, so the heat would transfer from this left part to right part due to the temperature gradient. So there will be a very much large temperature down here because I am adding heat at this point, right? So there will be a large temperature at this point, and there will be ambient temperature at this part of here. So that's a large temperature gradient. That's a normal way in which heat transfer occurs due to temperature gradient. There should be a difference in temperature not to have a heat transfer. So the heat transfer takes place uh, along the material by conduction because the same material is of in from this point to this point, the heat transfer occurs by conduction. Okay, by the transfer occurs by the same material. So that is obviously conduction, right? So after when the heat transfer heat uh, take at this point, okay, after the heat achieve this point, from then it could be anything, right? It could be an atmosphere, it could be any fluid. So there's a transfer of heat from an material to another fluid, different medium. So that is obviously convection, right? So the conduction is take place by the considering the surface resistance, that is 1 by HA. We already learned this formula 1 by H and L by K in the previous classes, the flat surface. Okay, that's the resistance for convection and conduction for flat surface. Here it is the L by K. This is the internal resistance developed inside a plate for the case of heat transfer, and this is a surface resistance due to convection. Okay, 1 by HA. So this is the surface resistance, and this is the internal resistance. So for lambda analysis, we are considering that internal the body will be having infinite thermal conductivity. Okay, that means how does that achieve a body having infinite thermal conductivity? The volume to area ratio should be should be having a very large in proportion. Okay, so suppose for we take plates and metallic wire. Okay, so you see the thermal conductivity with the surface area that is large in proportion to the volume. Okay, that's a reason we'll be having a very large thermal conductivity. Okay, compared to the volume. Okay, volume to area ratio would be very much there's a large difference down there. So process in which the internal resistance is assumed negligible in comparison with the surface resistance. That's Newtonic heating or that types of heating. Okay, when the internal resistance is very much smaller compared to the surface resistance, it is Newtonic heating or cooling process. The temperature in this will be obviously uniform. Okay, and this whole analysis will be lumped parameter analysis. Okay, so in lumped parameter analysis, the energy at any time of the heat transfer, okay, energy transfer, it would be function of the temperature and the total heat capacity. Okay, so this is a basic assumption or a basic principle behind the lumped parameter analysis. If you look further, as you can see down here, so let's take a scenario. we are having a body whose initial temperature be Ti throughout. Okay, that's a uniform temperature distribution. We have a body which is having an initial temperature throughout and which is placed suddenly in ambient air. Okay, suppose it's having a 50 degrees Celsius temperature at any point. Okay, throughout the body, it's a uniform temperature. So you take any point of that body, will be having same 50 degrees Celsius, and I'm say, placing it in ambient temperature. Suddenly temperature change, right? So ambient temperature could be 30 degree, 28 degree. So suppose I'm suddenly placed it in the ambient temperature or any liquid at a constant temperature Ta. Okay, Ta be any ambient temperature means Ta. So suppose not an ambient temperature or any other constant temperature. It should be a constant temperature. It should not vary. Okay, that should be that the temperature at which the body is placing should also be a very constant temperature. Okay, the transient response of the body can be determined by the relating the rate of change of the internal energy with the convective exchange of heat. Okay, obviously there should be a heat transfer. If I am placing 50 degrees Celsius body in a 20 degrees Celsius or the any temperature below it, obviously there should be heat transfer from the body to the that like at ambient temperature, right? Should it will occur. So the condition we are taking there, the change there would be an internal change of the body, right? So that the rate at which internal energy change should be we are relating with the convective exchange. There is convection because from the heat transfer takes place from the on between the different body, right? From the body toward atmosphere temperature or any fluid ambient conditions, so there is convective heat transfer case, and that convective heat transfer is equal to the rate of change of internal energy. So the body's internal energy, and we know internal energy is a function of temperature, right? So there would be a change in internal energy, and that internal energy change, the rate of change of internal energy, it should be equal to the convective exchange at the surface. Okay, surface. So this is a basic assumption we're taking for formulating the equations for lambda analysis. As you can see, this is equation that the internal energy change will be the convective transfer equation. So it's a delta T. Okay, so T is the initial one or any temperature, and T is the ambient one. So this is I can write this as rho Vc dt by d rho. Okay, so rho is the tau. Okay, this is the tau. Tau is the time. Okay, so this tau is the time. So okay, we have a this is the equation change in energy. Rho Vc dt by d tau equal to Hs T minus Tm. Okay, so T is the temperature of the body at any time, not the initial temperature. This is the temperature of the body, that convective transfer temperature of the body at any time, and T is the ambient atmosphere temperature. Okay, rho is the density of the solid, V is the volume, C is the specific heat of the body. Okay, whatever body you are considering, the specific heat is C. H is the uh, surface conduction, right? It's conductance, surface conductance, the convective transfer coefficient, and T is the temperature of the body at any time. Okay, it could be not on the initial condition. T is the body at any time, and tau is the time taken for the heat transfer. Okay, so T is the tau is a, if suppose we are considering a temperature at a particular point, I mean particular time. Okay, suppose having up to 30 minutes or could be 15 minutes. Like how much time it will take for that temperature achievement? That is represented by so. Okay, so for the formulating, we have the final equation. This is the final equation according to lambda analysis, where theta is the temperature difference. Okay, theta is a constant we are assuming for formulation. It is a temperature difference. This is the temperature difference at any time. Okay, we are because as you can see, theta is equal to T minus Ta, and theta I is equal to Ti minus Ta. Ta is the same in both terms. So T is the temperature at any time, right? So obviously this temperature is also temperature difference at any time. Ti is the initial condition, temperature of the initial condition. So this is the temperature difference, initial temperature difference. We won't be using this term because we need this for finding the numerical. So the actual equation is simply T minus Ta the whole divided by Ti minus Ta equal to e raised to minus Has tau rho Vc. Rho V into C. C is the specific heat. Okay. So this is the equation according to lambda analysis. Okay. Next, if you look at the nature of the graph plotted between temperature and time in the case of lambda and also neutron heating. So we already mentioned neutron heating or cooling due to the very large of surface resistance compared to the internal resistance. So from the equation, we have this formula right e raised to. So this formula rho Vc HAS. This is for transient temperature response and it is represented by rho Th. Okay, it's a thermal time constant. Okay, just keep that in mind. And one important thing we have to do is we have to, when you're doing problem, you have to find the value of Biot number. Only if the Biot number value is less than zero point 0.1, then only we can apply Newtonian cooling or heating. I means I can use that general equation. So we have to find Biot number before solving the problem. HLC by K. So this is the equation. We have K, it would be in the given condition, will be having K and H, but you have to find LC. LC is called the characteristic length. This has to find before solving the problem. Only then I can find out whether the value is less than zero point 0.1 or not. Only then I can use the general equation according to Newton law. The equation I just explained earlier. If I want to apply this equation, I need to find LC. Okay, LC is characteristic length. That is the volume of the solid by surface area of the solid. So this is the equation, LC's equation for different geometry. This is for flat plate, cylinder, sphere, cube. For flat plate, applying the volume by area, I can see that volume is length into breadth into height. And area that is not simply breadth into height or length into breadth. It's 2 into breadth into height. The reason why there is a 2 because we are considering the both side. So you should always multiply 2 in the case of flat plate, not simply just simply length into breadth or breadth into height. You just have to multiply with 2 here because we are considering the two side. Okay, so the simple formula or simplified formula is simply L by 2. So not to find the characteristic length, just length by 2, semi thickness. Okay, if you have the length, just take the half in order to find the characteristic length of flat plate. Okay, L is the thickness here. L is the thickness. Don't just interchange it. L is the thickness and B is the width and H is the height. Okay, if we have the thickness, then take the half and to find the character length of flat plate. Similarly, these are the equation for a cylinder. If you have the radius of the cylinder, just take the half. If you have a sphere, 1 by 3 of the radius of the sphere will be the characteristic length and cube L by 6. Okay, if you have the side of the cube. So this value, you have to find characteristic length, that means you have to find Biot number. Only if the value of Biot number is less than zero point 0.1, you can use that law of Newtonian heating or cooling condition. That means you're applying the basic equation. Okay, so we have to find the characteristic length. This is the equation for characteristic length for different geometry. Okay, that's all about lambda analysis. And next video I'll be explaining to solve different problem. Okay, according to lambda analysis, how do you solve the different problem set of lambda analysis? Okay.